Hello to everyone. First of all, I wish to thank the organizers for having me here, and let me present this work done together with my friend Alberto Tinaburi. This study deals with density waves in crowd assemblies, emerging patterns and agent-based modeling. Just take a look at this work. The study deals with the patterns that may appear due to crowd assemblies where people comes in contact. You can see just pictures here, the upper part of the screen, longitudinal waves where the colors mean a difference in densities. The magenta are higher local densities, and in the bottom part you see the same for radial waves that have emerged. Outline of this presentation. We will take a quick look at the complex systems and the way we can deal with them in a synthetic manner through the so-called ODD protocol. Then we'll move to the behavioral rules and constraints that are involved in the NetLogo platform we have used. Then we'll go through the simulations and the patterns emerged, and then a quick look at the conclusions and the future work that we have scheduled. Complex systems, because we are updating our research program for exploring crowd and fire dynamics as complex systems, where the interactions of the single entities in the system interact so that patterns of behaviors may emerge at the overall set level. The aim of the study is to explore density waves that may appear in crowd assemblies, and they will be started depending on initial and boundary conditions. We have modeled a crowd of people that gathers inside a two-dimensional square domain at the start with variable initial densities that are set up to explore different initial conditions. By the time the movements in the crowd driven by some event may vary the density, we can go from lesser global density values to higher local density values. An event, for example, due to the desire of reaching some spot for increasing entertainment or the need for escaping perceived critical situations. The behaviors of the people as individual from reactive to adaptive define so the contact pressures among the persons, where upper thresholds that may be tolerable are critical parameters. So the people's behavior as a whole translates into the pressure density waves propagation. We try to set and define suitable metrics and behavioral rules, and hopefully with counteracted actions to recover to better conditions. We use the approach of agent-based modeling through the NetLogo open source platform that is a tool well suited for studying complex systems like this one. The ODD protocol describes in a synthetic manner what we have done. It is divided in three parts: overview, design concepts, and details. The overview. The model tries to explore the emergence and the evolution of crowd density waves. The waves develop while the contact pressure among the persons over a unit area begins to increase, and no relief to reduce the pressure is available. The persons come into contact, ever increasing into same unit area with insufficient space to collect them at a comfortable level. The only way to stop pressure from increasing is either limiting the number of persons per unit area or let some persons quickly move away from the overcrowded area once the event triggers the onset of the wave itself. The design concepts. The model aims at studying some basic aspects of these complex systems, for instance, interaction, adaptation, or properties, emergence, self-organization. We use two kinds of NetLogo agents, the patches for modeling the world and the turtles for modeling the people. Depending on the number of persons over a patch, a global density is initialized in the world. When the number of persons over a patch increases, the patch's colors vary in accordance to let appear the way the density changes. In that way, we can also track local densities. The density wave emergence can thus be tracked as the evolution of the colors in the patches. The patches are static agents that do not move in the world, while the turtles are moving agents. The details. The initialization is done by designing the environment and the agents. We did not use any recorded data to start the model, but we used some estimations from personal experience and literature survey. The input data of the environment are the geometry and the effects. And the input data of the agents are the position and the characteristics. The submodels refer to the actions of the agents, reactive, adaptive, and also to the effects of the environment. The rules are quite a few, just needed for starting actions and activate what happens in consequence, with the intent and hope or letting the system evolve by itself to some state, with some pattern that may be also observable when emerged. But what kind of patterns do we mean? We refer to some kind of pressure density wave patterns due to the contact in the people of the crowd in the environment. In order to describe the behavioral rules of the agent set of the system, it is convenient to adopt an agent-centric viewpoint. So, think if I am a patch or if I am a turtle. If I am a patch, what do? I help set the world, its domain side, internal area and perimeter boundaries. I am always 1 meter squared independently of the domain side chosen, so a suitable metric may be devised. When I represent a boundary, I can be in a closed or open state, and I have an option also of adapting my opening to some effect due to the turtles. I can always accept turtles on me. I set and change my color depending on the number of turtles on me, up to a limit threshold. And if I am a turtle, what do? I model a single person. I can move or not. I change my heading. I may get closer and closer to other turtles, up to a limit threshold in the same time window. If I behave as reactive, my action depends primarily to some event occurred in a past time that may have affected me. And if I behave as adaptive, my action depends both on some past event and on some choice or forecast I make to try to get to a better future condition for me. Once deciding the setup, the world with patches and turtles to run the simulation, the model is programmed to code the roles, design apply control tools to manage any operation needed in the work. The metrics compare results, analyze data, explain attributes, and are based on a continuous space and discrete time frame. Several runs of the same baseline setup are needed to take into account, at least in a basic form, stochastic effects. Two setups for the model are chosen. The first one is to study waves appearing in the form of longitudinal pressure waves where the contact is along some preferential direction. Second type of setup relates to waves in the form of radial pressure waves where the contact appears as related to a central spot. In both cases, we try to take into account the critical parameters that characterize the response of the systems, such as clusters of sudden increased local density, available spots to relieve proper pressure. Furthermore, we try also to take into account if there is some threshold marking a sudden change of behavior, for example, jumps or fall, and so forth. Just to get started for the model, we of course programmed what is needed, the setting of the world, the dimension, the time unit length of the simulation run. This is important. The tick. The tick is the discrete time unit clock. The simulation run advances of 1 tick whenever all of the agents involved have performed their task. We also use monitors and plots to get dynamically variable information. The simulations present similarity and differences between longitudinal and radial pressure waves. Similarities are initialization of the world, is the same world. It's interesting to see that we set 2 initial global densities for comparison of 2 and 1 person per square meter, for examples, the coloring of the patches, what is updated, what we can get from monitors and plots. Differences of the 2 types of setup regards essentially patterns of simulation from clusters and move clusters in the radial case and some behavioral rule. We can have a quick look at the behavioral rules for actions in the longitudinal and radial patterns. So the actions performed by which agent set and what to do, setting the world, to move to recover the density rendering in the longitudinal patterns, and radial patterns that are different, for example, because there is the forming and moving clusters and escaping from the world with some different, of course, behavior. Essentially, in the second part of the table radial patterns, we added an adaptive behavior where there is a possibility that the boundaries get opened when they can sense turtles that reach the threshold, and so they get opened. For both types of patterns, we grouped simulations to compare the study based on similar setup with different time windows of runtime and global density of 2 or 1 people per square meter. Some slight differences appear due to the random actions of the evolution dynamics. And any of these simulations show how the patterns are starting from substantially similar conditions quickly may slightly vary depending on the effects on the systems of the single actions during the runtime clock. We here show some results from the simulations where we show some figures, the 2-dimensional domain and the metrics used. The colors in the domain represents the color of the patches that map the local densities updated on the run, with white patches with 0 turtles on them, green patches with 1 turtle on, yellow patches with 2, orange patches with 3, red patches with 4 turtles on, and magenta patches with more than 4 turtles on them. Actually, they can be varied to study different conditions. Here we have a look at them. Longitudinal waves emerging patterns at the end of 100 ticks of runtime. Initial global density of 2 persons per square meter. The magenta color shows the way the pressure is set in the upper part where the people remains with more high value of local density. And the situation is better when we reduce the initial global density set up at 1 person per square meters. And you see also the way there is a variation in the colors in the mapping. Same for runs where we let the system evolve for a longer time of simulation. We refer here at 1000 tick and run time. And also you see the way the patterns present themselves at the view. The same thing when we reduce the initial global density to 1 person per square meter. And same for radial waves emerging patterns with 2 people per square meter density set up at the start, with simulation at 100 ticks of run with adaptive boundaries, having 4 persons per meter square as limit threshold to get them opened. The same thing for initial global density of 1 person per square meter, or even better, of course. Again, letting the system evolve for a longer time, every turtle has escaped freely from the world. At the end of the 1,000 ticks now of run completed, with 2 and with 1 person per square meter. And what to do again, just to show the evolution of the dynamics of a single run, we have just presented another kind of figure type, so we can see from left to right the start and the end of the simulation for longitudinal waves at 2 people per square meter. Here essentially the boundaries are always closed and there is a reactive behavior of the agents, of the turtles. Again, reducing initial density is beneficial. And the same thing for radial densities of 2 and 1 persons per square meter initial global density with a 4 person per square meter limit threshold boundary to get them opened. What to do in conclusion in future work schedule. Some parameters show greater effect and then others. Initial global density, time the boundaries can get open, and the limit average density threshold. The metrics show overall trends and sudden changes in the evolution of the dynamics of the system, as you can see here in the picture in the end. So future work is scheduled to expand the groups of simulation, examine similarities, differences, and the effect of critical parameters at input and output. We thank you for this time given to us. See you.
Thank you for the talk. Let's see if we have any Q&A or chats coming through. And meanwhile, any questions here in the room? Okay, we have a couple. Back to Dan.
Where was the question?
Dan.
Dan.
Thank you. Do you have any correlation with real data? I mean, how does this actually apply to the real world? I know that crowd crush is a problem, and I know we have not really worked on simulating it, but some tie to some real data would really help me understand what's going on.
Thank you for the question. We have started this work just thinking of it. We have explored the way in this tool we can manage overall shapes and patterns appearing, because we know there are several local densities that have been reported both in the literature survey and also from imaging all over the world. Our first issue of concern is the way of mapping an overall behavior. And for that reason, we set up a simple threshold, and as you may have seen, we have set at 4 people per meter squared as adaptive boundary opening. But there may be clusters forming at higher local density levels. This is totally, anyway, disjuncted. It is not considering the physical effect, of course, because the first kind of studies like this one is the way we can use some tool to represent the overall shape emerging for what may have been happened, and we can see from real images all over the world. And in this part of our study, intentionally, we cannot make any considerations about number for local densities for 2 reasons, essentially. The first one, we are not studying the effect because we have to take into account physical effects based on other informations that are not dealt with here. And secondly, we have to deepen the way the metrics can be chosen, because we have used some metrics just to start the work, but we have to deepen this one if there is some more possibility to add some other metrics. I hope this has been understood.
Other questions? No? Doesn't look like it. Okay, well, thank you very much for your talk and your presentation. Thanks for joining us, and have a good afternoon.
Thank you, Chris, for all, and thank you for this opportunity. Bye-bye. Ciao.